Hey guys, my name is Eddie the Electron, and today I'm going to draw my life. I'm going to outline my journey of self-discovery and how I ended up in the best relationship of my life. First, a few things about me. I'm billions and billions of years old. I've been alive since the beginning of time. I've had a pretty lonely life until I found the one. I now live in a beautiful methane molecule in an electron pair, but my life wasn't always so great. So when I was young and naive, living alone in a carbon atom, I believed finding love was simple. I like to believe the simplicity of the valence bond theory, where love can easily be found when two atomic orbitals overlap, pairing up two lonely electrons and forming a covalent bond between two atoms. The possibility for bond formation exists when two atoms can approach each other in such a way that occupied orbitals with similar energies are able to come into contact or overlap. The greater the amount of overlap, the stronger the bond. The lower the energy of the atom, the more stable the relationship. That's how my friend Larry, who lives in a hydrogen atom, found his partner. Larry was living all alone in a hydrogen atom with a 1s orbital, all to himself. Then another hydrogen atom came along, and it was love at first sight. Their orbitals overlapped. His spin was compatible with the other electron's spin, so they formed a single covalent bond. Romantic, right? I see electrons get paired up like Larry did all the time, and not even just between electrons and s orbitals. It happens with s and p orbitals too. Those relationships are called sigma bonds. There's also another type of relationship that can be formed, but I'll get back to that. All of this is great, of course, but I still couldn't understand the bond lengths and the angles between the bonds in molecules with more than two atoms. The geometry of the molecule also didn't make any sense. As an electron in the 2s orbital, I couldn't form the same bond as the 2p electrons, but in order to form compounds like CH4, where all bond lengths and angles are equal, I had to. But how? Love was becoming more and more complicated than I ever thought. To get some answers, and hopefully to find the one, I talked to a goddess of chemistry, Savita Paul. I heard she was the best matchmaker in the business, so I told her my dilemma, and she said, "You are a stupid oaf, Eddie, but I will help you since I am a true goddess. If only you were as smart as my other darling student. If only you were a couple shades browner." Then she went on to explain a concept called hybridization. She told me what I had to do to find love. She told me I had to somehow blend the higher energy levels with the lower ones to create this intermediate energy level. These new orbitals would be called hybrid orbitals. She told me the story of her previous clients, who now live in BeCl2 and BCl3. The electron who now lives in BeCl2 used to be a lonely electron, just like me. She lived in beryllium in the 2s orbital, and she just couldn't form bonds with other electrons. In order to create this new hybridized orbital to get the electron of her dreams, who lived in a chlorine atom, she had to jump to the unoccupied 2p orbital. She had to do this because the chlorine atoms would need two unpaired electrons in order to bond, but she was stuck in the 2s orbital with her friend. So she left her friend in the 2s orbital behind and ended up forming two new orbitals. These two orbitals were called sp orbitals. These new lobes are larger than the original s orbitals and therefore can form larger overlaps with other orbitals, making the bonds stronger and more stable. These lobes are pointing in opposite directions, giving the molecule a linear formation with bond angles of 180 degrees. And the energy required to form these new hybridized orbitals is offset by the energy released by the formation of the chemical bonds. She formed a cozy spp bond with a kindly chlorine atom, and she's still happily living there. Savita sees her from time to time, but she's stable now, so she doesn't react. So that was her story, but let's talk about the electron who now lives in BCl3. That electron lived in a lonely 2s orbital in a boron atom, but then jumped to a degenerate orbital of one of the unoccupied 2p orbitals. His story is similar to the electron in BeCl2, but the difference is that there was one unpaired electron already in one of the degenerate 2p orbitals of the boron atom. So when the electron from the 2s orbital jumped up to one of the p orbitals, there were three hybridized sp2 orbitals formed. Hearing their stories, I was inspired. For the first time in my life, I felt like I could do anything. I've been in love with this electron in a hydrogen atom forever, and it was my time to shine. So I did it. I got excited and jumped from my lonely 2s orbital home in my ground state to an unoccupied 2p orbital. Then, the 1s and the 3p orbitals mixed and formed four sp3 orbitals, with large lobes forming a tetrahedral formation and a bond angle of 109.5 degrees. This made me an officially unpaired electron, a true bachelor, single and ready to mingle. The hydrogen atom approached and my life changed forever. We connected right away. You may even say we had chemistry. My hybridized sp3 orbital overlapped with her s orbital, giving us the chance to pair up and be together forever. Both of our nucleus parents approved, and the attraction kept us all together. Me, my electron, and our two nuclei were so happy. We did everything together. But after a while, I started feeling a little incomplete. I realized that while I was so happy in my relationship, I still needed to make something of myself. So I called up the goddess again. I explained that I wanted to help other electrons out there find love too. She said, "Oh, hello Edna. Eric? Ethan? Oh, right, Eddie. Hello, Eddie. Of course I will help you. I just love to see your passion for chemistry. Now let's get to work, you stupid oaf." So this is what I learned. There are even more types of hybridized orbitals. In molecules such as phosphorus pentafluoride, there is sp3d hybridization. That type of hybridization includes the mixing of the 3s and 3p electrons with an empty 3d orbital to form 5 sp3d hybrid orbitals. Here, a paired electron from the 3s orbital jumps to an intermediate energy level to meet the empty d orbital, and all 5 valence electrons form 5 sp3d orbitals. These 5 electron domains give the molecule a trigonal pyramidal molecular geometry with bond angles of 120 degrees and 90 degrees. The final type of hybridization can be seen in sulfur hexafluoride, where the hybridized orbitals are formed between the mixing of 2 electrons from the 3s orbitals and 4 electrons from the 3p orbitals, making 6 sp3d2 orbitals. Again, the paired electron in the s orbital jumps to one of the d orbitals, and one of the paired 3p electrons becomes unpaired, forming the 6 new hybrid orbitals with the 4 unpaired electrons, with an octahedral molecular geometry and a bond angle of 90 degrees. The goddess also told me that it's important to remember that some relationships are stronger than others. Remember when I mentioned sigma and pi bonds earlier? This is where they come in. Sigma bonds occur in single, double, and triple bonds. This is when 2 orbitals overlap head-to-head directly parallel to the atomic nuclei. They are the strongest type of covalent chemical bond. The other type are pi bonds, and they only occur in double and triple bonds. This is when 2 parallel p orbitals stay unhybridized and undergo sideways overlap. Since the nuclei are not shielded like in sigma bonds, the electrons are further away from the nucleus, and therefore more polarizable and chemically reactive. The pi bonds form areas of high electron density above and below the line of the atomic nuclei, and they're perpendicular to it, not parallel. All double bonds are formed by 1 sigma bond and 1 pi bond, which is above and below the bond axis. All triple bonds are formed by 1 sigma bond and 2 pi bonds. The length of the bonds also comes into play here. The single bond is longer than the double bond, and the double bond is longer than the triple bond. The sigma bond is also stronger than the individual pi bond. All this new information got me thinking, why were some relationships stronger than others? What are the conditions needed for sigma and pi bonds? Well, for a molecule with only single sigma bonds, the orbitals have to have sp3 hybridization because you need to have 4 orbitals, each with an unpaired electron in order to bond with other atoms. In order to make a molecule with a double bond, you would need to have sp2 hybridization because you need to have an unhybridized p orbital to make the pi bond. Following this logic, you would need sp hybridization in order to form a triple bond, because you need 2 unhybridized p orbitals to form 2 pi bonds. After learning all this information, I began my journey of helping other electrons find love, just like how I did. My hardest matchmaking job was probably when I was faced with a puzzle that no other matchmakers could figure out. There was a certain compound called benzene, and the electrons in that molecule were so happy, but no one knew their secret. I had to figure it out so I could help other lonely electrons find love. It was my moral duty. Benzene is an important organic chemical compound with the chemical formula C6H6. The benzene molecule is composed of 6 carbon atoms joined in a ring with 1 hydrogen atom attached to each. I called up my own buddy Frederick August Ticulet, who told me his theory on the structure of benzene. He was kind of a pothead though, so I'm not sure how much I could trust his theory. He figured that benzene's structure contained a ring of 6 carbon atoms with alternating single and double bonds. I went with his theory for a while. I mean, it made sense. But then I started having a few questions. Maybe it was the drugs we were doing together, but it didn't quite make sense. If his structure was right, then how could the bond lengths all be equal? Single bonds are supposed to be shorter than double bonds, so it doesn't make sense that all the bonds are equal in length. Also, after doing a few experiments, I found that benzene was more stable than a typical unsaturated compound, or compound containing double or triple bonds. To explain all this, I found the following. First, when the benzene molecule reacts with hydrogen, when it is hydrogenated, the heat produced was much less than what would be expected for 3 double carbon-carbon bonds. The molecules showed extra stability, and the resonance energy, or the difference between the calculated and observed heat of hydrogenation, was very high. Because it doesn't behave like a typical unsaturated compound, it must mean that it isn't one. The bonds must then exhibit something called resonance, in this case, when 2 carbon atoms share 3 pairs of electrons in total. These bonds are sigma bonds, formed between the hybridized sp2 orbitals in each carbon. One orbital will overlap with the s orbital of a hydrogen atom, one will bond with the adjacent sp2 orbital of the carbon atom beside it, and the third will participate in resonance. The remaining delocalized p orbital electrons, who do not take part in hybridization, form a pi bond cloud above and below the carbon ring, which is held together by sigma bonds. These p orbitals are overlapping everywhere, and all 6 carbon atoms share the 6 delocalized electrons. They belong to no one. These electrons aren't ready to settle down, so they like to go more from atom to atom, if you know what I mean. They show these bonds as a circle in the middle of the carbon hexagon. This also explains why the bonds are of equal length, as resonance bonds have a length that is in between the length of a single and double bond. So the modernized structure of benzene would be drawn as a hexagon with a ring in the middle, instead of having alternating single and double bonds. In reactions, the benzene molecule also does not undergo any additional reactions other than the substitution of a hydrogen atom for another atom. This is because the relationships between the carbon atoms are so stable that to react with another atom and to break the bonds would require great amounts of energy. They're just so happy where they are because of their strong covalent bonds and their sharing of the 6 electron children that they don't want to change anything other than their side hose. And this brings us to the end of my story so far. You guys know quite a bit about me now. I just can't wait to see where life takes me in the future. Now that I'm armed with the knowledge and secrets of what makes a strong, stable relationship, I can go on and help more and more electrons find love. See you later, everyone!